For the video lesson notes that we're looking at here for 6.4 and 6.7, we are dealing with infinite geometric series, as well as just the use of summation notation in order to find a sum. So the funky looking E letter that you see right here is the capital Greek letter sigma. So sometimes this is referred to as sigma notation or summation notation, same thing, simply because we are finding a sum. So anytime you see that letter for these, that is dealing with a sum or a series. So for this, simply all you're seeing down here on the bottom is what term you are supposed to start with. So this is telling us to start with a term of 0 and to end on a term of 2. So we are finding the sum of terms 0 through 2 according to this rule. So all I would have to do to figure this out is plug in 0, 1, and 2 in for n. And so that's what you're seeing right here. We subbed in a 0, a 1, and a 2. Those were the three results, and if we just add those together, we get a sum of 57. So that's certainly one way to do that by hand, and in a case like this, that's easy to do because there's only 3 terms. But what happens when you run into something a little larger for like 40 terms, you wouldn't want to have to do all that by hand. So there's a couple things you can do to save yourself work on these, and the first would be with the use of a formula. If I start plugging in just the first couple of numbers, plug in a 1, a 2, and a 3, I can see that there is an arithmetic pattern taking place, right, as I am adding 20 every time to get the next term. And so one thing I could do is I would take the S of n formula for an arithmetic series and plug into that. So we know that there are 40 terms because we're doing 1 through 40. So we plug in a 40 for n. We have the first term, and then this is the value of the 40th term. So when you plugged in a 40, you got this value. And so here we are with the formula setup, and we can get that solution right here. In a case like this, if I start plugging in numbers like 2, 3, 4, and 5, so these are just terms 2 through 5, you don't need a formula for that. There's only 4 terms. So you could just plug in the 4 numbers, get the 4 results, and add them together to get your sum. That's an option. In cases where you have more numbers and you don't really want to do them all by hand, you can start looking for formulas. So if you recognize on this one, if I start plugging in some numbers, these are the results that I get. This was the first term, second term, third term. You can see that they are doubling every time. And that comes from this guy right here. We have a common ratio of 2. And so because of that, I have a geometric pattern on this. And so I could use the geometric S of n formula, like you see right here, in order to get this sum of the first 10 terms. And so on some of the smaller ones, you can do them by hand if there's not that many terms. You can use a formula. But here's another way, and this is a cool feature of your calculator that I can show you. So especially on some of the newer calculators, this is even easier. When it comes time to taking a test in my room, you're always welcome to borrow one of my calculators, and so this would be available to you. But if you want to do any of that, just pure calculator, if you go under the math button that you see right here, if I go under math and I scroll down to summation, I can sub in all that information into this to get my sum. So I'll show you one example here, but I'll grab this one right here. So if you're looking at this scenario, so if I had n equals 1, so keep this one in mind. I'm going to make this calculator screen bigger so that you can see what I'm doing. But I'm going to plug in n equals 1. I got 10 at the top, and then I got 9 times 2 to the n minus 1 right here that's going to go in for that spot. So I'm starting right here with n equals 1. So for this one, you're going to use this guy as your variable. It doesn't matter if it's x or n. It's irrelevant, so just hit that button. And we said we were starting with the first term. I'm going to hit over. That takes me up top. We said we were going to go through term 10. And then over one more time. And the rule that we saw was 9 times 2. And I'm going to raise that to the n minus 1 power. So there's my setup right there. All I have to do is hit enter and I get the same sum. So that's a way you can take advantage of that on your calculator, which is easy to do. If you look at example number 5 right here, Notice on this one, here's the change, and here's what we're getting into for the last part of these notes. This one doesn't define an ending. It just simply says we're going to go on forever. So we're going to start with the first term, and we're going to head towards infinity. As I start plugging in a few numbers, right, you can see these are just the first three terms. Because my common ratio is bigger than 1, these numbers would simply grow as time goes on. And so we get this infinitely large sum, so there's really no way to find a specific sum in a case like this. If you look at something that we did pretty early on, like I think this was like the first day review worksheet where you dealt with these recurring decimal problems where you take this and put it into fraction form. This is another way to do that. So if you think of this as an infinite geometric series, so notice the ... meaning it goes on forever. So here's the first term, would be 0.3, and then 0.03, 0.003, right? And if we keep doing that pattern, so the 0.3, 0.03, 0.003, if you start adding those together, you start getting 0.3 repeating forever. And so we know that this is the same thing as having 1/3 as a fraction. And so this is one way of getting fractions like this for repeating decimals. But really all this is to lead you into our final formula here for our geometric stuff. So if you look again at your formula packet, there's one more formula in here that you want to be aware of, and that's this one right here. So notice the infinity on this. So this would be the sum of an infinite geometric sequence. So a couple things have to be true. It's got to be geometric for one. And the second thing that has to be true is this idea right here. So your common ratio has to have an absolute value smaller than 1 in order for this to work. If it's not smaller than 1, it does not converge on a specific number. The numbers simply get bigger and bigger and bigger, and so really you're just approaching infinity. And you saw that with this example up here, right? This was a common ratio bigger than 1, and so because it's bigger than 1, the sums just get larger and larger and larger. You're not approaching any one specific number, you're just approaching infinity, and so there's really no way to get a finite sum on that. But if your common ratio is smaller than 1, then you can get an infinite sum, and it's really not a specific value. It's what number we are approaching as time goes on, or as the bigger your results get, you are approaching some number. And so this is kind of the derivation of where this formula comes from, but really all you need to know is the formula itself. And it's a simple one. It's just first term over 1 minus the common ratio. So there's only two things you would need to know: the first term and the common ratio. So if you look at a case like this, so here you can see that our first term is 100, and then the numbers are decreasing by some fraction. And in a case like this, if you weren't sure what that common ratio was, remember you can take any term and divide it by its previous term to get your common ratio. So if we did 90 over 100, we get a common ratio of 0.9. Because 0.9 is less than 1, then this becomes possible. If this were larger than 1, we would have to say it's not possible. So we just plug in the numbers. You got your first term, you got your common ratio, and we get the sum of, technically, as this pattern continues, it does go on and on forever. You can see by the ... that this is infinite, and so you can't really get a true sum to this, but what we get is the number that we are approaching. And so if you saw this graphically, you would see that we basically have an asymptote at this value. This is the number that we are approaching as our sums get larger and larger and larger, even though we would never actually land on this number. Same thing on this one. Just another example. This would be a great one to pause and give a try on your own if you want to pause the video. But again, same on this one. We have, same with these last two that you see right here. Just plugging in a first term and a common ratio to get our sum. Be careful on the double negative. A lot of people get these wrong because of the double negative, so just be careful on that. You do get a plus out of that. And so here's what that infinite sum would look like. And then same thing on this, just be careful with the fractions as well. So you got your first term, common ratio. Remember, if you are not sure what that common ratio is, take any term, divide it by its previous term to get your common ratio. And so that's what you see taking place right here. Common ratio becomes 1/2. So I got your first term here, you got your common ratio here, and the sum is approaching 1. Something we mentioned in an earlier video is the idea of a limit. This here's kind of the connection to these infinite sums and limits. As time goes on, as things get larger and larger and larger, the idea is what number are you approaching? Here's kind of some notation just to give you a little introduction to this, but this is the limit as x approaches infinity of this function. So when we say as x approaches infinity, we're simply saying that x is getting larger and larger and larger as time goes on. And so what would the result look like if x became really, really large? If this became a really big number, let's just put in a million. So if this was 5 million plus 16 over 2 million plus 7, as this number becomes extremely large, these guys become pretty insignificant the bigger this gets. And so we basically would be reducing this fraction. 5 million over 2 million is just 5 over 2. And the bigger x becomes, the less significant these become. And so we are approaching 5 over 2 the bigger x gets. And so that's the way we would see the limit of that function as x approaches infinity. We get closer and closer and closer to a limit of 5 over 2.